Hello, welcome to Matrices 1.1 on linear transformations. This is going to be a series on matrices where we're going to take a look at matrices from the perspectives of linear transformations and vector algebra. So we're going to start off with matrices 1.1. We're going to look at the definition of linear transformations as well as looking at its general forms and a geometric representation of what exactly it does. Okay, so starting off with the definition of a linear transformation, here we can see that a linear transformation is just any function f with these two properties. So firstly, we have to get the same result whether we apply f after addition or before addition. So here we have that f of x plus y equals f of x plus f of y. And this is the distributive property of f. Secondly, we have to have that if k is some scalar, so k is some real scalar, then f of k times x is always going to be equal to k times f of x. And I'm going to refer to this as the commutative property. I'm sorry if the text is a little bit jagged. I'm still working out the kinks in the program that I've written to record all of this stuff. Okay, so now we know what the definition of a linear transformation is. Let's move on and let's try and figure out exactly what they are. So we'll try and find some general forms. So what do we mean by a general form? So when I talk about a quadratic, I'm talking about a certain class of functions. Same as what I'm talking about a line, right? I'm talking about just about some general class of functions. And the way that we describe what we're talking about is we give a general form. So we say that the general form for a quadratic is a function of the form f of x is equal to ax squared plus bx plus c. And so this is our general form where we have that a, b, and c are just elements of the real numbers. Okay, and so this is the general form because it actually describes every single quadratic if we just vary the values for a, b, and c. Similarly with a line, we have the function or the relation y equals mx plus c, and you've probably seen some variations on this. And so here we would have that m and c parts of the real numbers. And so these are the general forms. And so we're going to try and derive something similar. So first off, we're going to start with what the general form of a linear transformation is in one dimension. So from one dimension to one dimension. So let's suppose that f is a function from the real numbers to the real numbers, which is linear. So that f is a linear transformation. Well, if we know that, then if x is some real number, then f of x is going to be equal to f of x times 1. And remember here, if we look back at the first property here, or the second property rather, the commutative property, then we can just pull this x that we have here outside the front of the f, just like we did here. And so that means that that is equal to x times f of 1. But f of 1 is actually just some constant. So therefore, if we have a linear transformation from one dimension to one dimensions, it must be of the form t of x equals just some constant. So if we called f of 1 k, then that would be t of x equals k times x, which just looks like a line. Looks like a line passing through the origin. And so this is our general form for a transformation in one dimension. Okay, so what does it look like in two dimensions? Or from one dimension to two dimensions? Well, just like we did just now, we would have that if t was a linear transformation from one dimension to two dimensions, so t goes from r to r squared, then t of x is equal to x times t of 1. But in this case, t of 1 is actually a two-dimensional vector because it's part of r squared, because that's what we're saying here, that t is some linear transformation from r to r squared. So this is a 2D vector, and so we could let this 2D vector be a b. And so therefore, our general form becomes that t takes x to x times some vector, a, b, which is of course just some multiple of this vector a, b. So for example, 1 would get mapped to ab, 2 would get mapped to 2 lots of ab, 3 would get mapped to 3 lots of ab, negative 1 would get mapped to negative ab, and so on. So we kind of have this embedding of the real line where here is 1, 2, 3, negative 1, and you can see that's what our linear function from one dimension to two dimensions looks like. Okay, what about two dimensions down to one dimension? Same idea, but this time we're starting out in two dimensions. So instead of splitting x up into x times 1, we're going to be taking xy, and we're going to split it up into x times 1, 0 plus y times 2, 0. 2, 0, 0, 1. Okay, Now what this lets us say is that if we have some linear transformation from 2 dimensions to 1 dimension, so let's just say, suppose t maps from 2 dimensions to 1 dimension is some linear function, then we must have that t of x, y is equal to t of x times 1, 0 plus y times 0, 1. And of course, using properties 1 and 2, we can distribute this out into x times t of 1, 0 plus y times t of 0, 1. Now these here are just scalars because we have that t maps each two-dimensional vector to a scalar. So our general form is that t of xy is equal to some scalar a times x plus some scalar b times y. Okay, and so this here is this is actually the class of all linear transformations from 2 dimensions down to 1 dimension, because here you can see we have a vector and then we just have a sum of scalars, which is 1 dimension over here. Okay, so there's one more we're going to take a look at, or two more rather. One goes from 2D to 2D and one is from 3D to 2D. So if we're working in 2 dimensions to 2 dimensions, then just like before, we split up xy into x1, 0 plus y, 0, 1. But this time, t of 0, 1 and t of 0, 1 are actually going to be two-dimensional vectors. So these are 2D vectors, which means our general form then becomes that t is a linear transformation from 2 dimensions to 2 dimensions if it takes a vector xy to some combination of vectors x times a b plus y times cd. And if you wanted, you could multiply these out and add them together, and we get our general form becoming ax plus cy, bx plus dy. And so that here would be our form, this two-dimensional vector. And so this here is the class of all linear transformations from 2 dimensions to 2 dimensions. Okay, so last one, I promise. 3 dimensions to 2 dimensions. Just like before, we're going to split the vector up, but this time we have a 3-dimensional vector instead of a 2-dimensional vector. So t of, we're going to call it, well here, let's just firstly use a different letter. So suppose u is a linear transformation from 3 dimensions to 2 dimensions. Well, then u of some 3-dimensional vector, x, y, z, well, that's going to be the same as u of x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. And we can, of course, just like we did up here, distribute t over this addition and then pull out these multiples here, and so that we see that that's equal to x times t of 1, 0, 0 plus y times t of 0, 1, 0 plus z times t of 0, 0, 1. Okay, now each of these here are going to be two-dimensional vectors because t maps from 3D to 2D, so these are all 2D vectors. And so we can see here that just as before, whereas we'd have a linear combination of a, b, c, d, here we would just have 3 two-dimensional vectors, and that would be our general form. Okay, so how do we actually visualize these transformations? What really are they? Well, if we look at, just as an example, from 2 dimensions to 2 dimensions, we know that the general form is some function t, where t of xy is some combination of 2 vectors a, b, and c, d. Now, if we were to draw these vectors onto our graph over here, and we put a, b here, and we put c, d here, then we can see that our point xy gets mapped to x lots of our red vector plus y lots of our blue vector. And so we can see that, for example, like t of 2, 1, well, that's going to be 2 lots of our red vector plus 1 lot of our blue vector. And we could see that by doing this, right? We'd have 2 lots of our red vector and 1 lot of our blue vector. And so this would be our resultant vector here. And so we can see now that 2, 1 gets mapped to this over here. 1, 1 would get mapped here. And so we actually get this kind of grid that we get to draw over our original grid, which is kind of a So like if we were to see where xy went, we would just kind of look up what the point xy in our new grid corresponds to on our original grid. Okay, so just as we've gone over some of the general forms here, we're going to go over the true general form in the next episode. So we're going to look at just transformations from n-dimensional real space to m-dimensional real space. Hope that helped. I'll see you next time.